You know, when you picture a black hole, you probably think silent, right? A cosmic void that just swallows everything, sound included. But what if I told you that's not the whole story? What if they can actually ring? We're about to dive into some fascinating new science that's learning to listen for the universe's quietest echoes.
This sentence right here from the research paper, this is what absolutely hooked me. It's just such a powerful and honestly poetic idea. It paints this picture of these cosmic monsters, not as just silent destroyers, but as, well, as instruments, just waiting to be played.
That's the big question, isn't it? I mean, obviously space is a vacuum, so we're not talking about a sound you could actually hear with your ears. So what on earth are scientists talking about? Let's break it down. To really get what this ringing is all about, we have to start with this beautiful metaphor, the idea of a black hole song.
Okay, think about it like this. If you strike a bell, it vibrates, and that vibration creates a sound. A black hole, believe it or not, is kind of similar. When something disturbs it, maybe another black hole merges with it, or a star gets a little too close and falls in, the very fabric of space-time around it starts to wobble and oscillate. And that vibration is what scientists are calling its ring. And it's an absolute goldmine of information.
All right, so this ringing isn't just a cool metaphor. It has a specific scientific name. And understanding this term is really the key to unlocking this whole concept.
These vibrations are called quasi-normal modes, or QNMs for short. And honestly, the best way to think about them is as a black hole's unique ringtone. Seriously, just like your phone's ringtone is a specific identifiable sound, a black hole's QNMs are its unique signature, and they're determined by its most basic properties, like its mass and how fast it spins.
In this comparison lays it out perfectly. For a normal bell, we talk about its pitch, how high or low it sounds, and how long that sound lasts. Well, for a black hole, physicists talk about its oscillation frequency, which is basically its pitch, and its damping rate, which is just a fancy way of saying how quickly those vibrations fade away. The bottom line is, if we can measure these two things, we're essentially reading a black hole's cosmic barcode.
Okay, so black holes ring. That's cool enough on its own, but the research we're digging into today added another, even deeper layer of cosmic mystery to the mix: dark matter.
You might be thinking, whoa, hold on, why complicate things? Why not just study the black hole by itself? And that's a fair question. But the thing is, in the real universe, nothing really exists in a perfect vacuum. Black holes are surrounded by, well, stuff. And it turns out a huge amount of that stuff is dark matter.
I mean, just look at this breakdown of our universe. All the ordinary matter, the stuff that makes up you, me, the stars, everything we can actually see is only about 5%. That's it. A whopping 27% is this invisible, mysterious substance we call dark matter. So if we really want to understand how black holes behave in the wild, we have to account for the environment they're swimming in.
So here's what the scientists did in their theoretical experiment. They took these models of what are called regular black holes, which are really useful because they let you avoid some of the super messy physics right at the center, and they placed them inside a simulated environment of perfect fluid dark matter. This basically let them create a clean cosmic laboratory to see exactly how that dark matter affects the black hole. So, what did they find? When you submerge a ringing black hole in a sea of dark matter, what happens to its song?
The results were pretty wild. First, and this is good news, the black holes didn't just fall apart, they stayed stable. But here's the kicker: their ring changed. The oscillation frequency went up, which means it had a higher-pitched sound, and the damping rate increased, meaning the sound faded away much more quickly. The dark matter environment literally altered the black hole's ringtone.
And this gives us a super simple, clear visual of what's going on. A black hole in a vacuum has its own natural ring. But when you surround it with dark matter, that ring gets both higher in pitch and shorter-lived. It's a distinct, measurable difference.
Now, this is all fascinating theory, but what does it actually mean for us? What's the real-world takeaway here? Well, it might just open up a completely new way of seeing, or maybe I should say hearing, the universe.
So here's the crucial point. If we know what a black hole is supposed to sound like in a vacuum, and we can actually detect what it sounds like in reality, the difference between those two sounds could tell us about the invisible environment it's sitting in.
And this is the basic roadmap. Step 1, detect these vibrations, these gravitational waves, from a disturbed black hole. And hey, we're already doing that with instruments like LIGO. Step 2, compare that real-world signal to our theoretical models. And then, step 3,
any discrepancy could reveal the presence and properties of things we can't see, like dark matter.
And hey, you don't have to take my word for it. The researchers themselves say it best. Studying these quasi-normal modes isn't just some abstract exercise. It's a practical method for gaining real insights into the fundamental properties of our universe.
So the next time you think of a black hole, don't just picture a silent void. Picture a bell, waiting for some cosmic event to come along and make it ring. Because in the subtle changes of that fleeting, fading tone, we might just find the answers to some of the biggest questions we have ever asked.